Greetings everyone. Welcome to another installment of Quarantine 5114. We've been discussing the Neyman-Pearson lemma since the first day of class. We brought it up. This comes up in Stat 101. This is the whole thing about thresholding p-values. So p-value thresholding, what is it doing? If the test statistic that you derive came from a likelihood ratio test statistic, it's going to have minimal type 2 error. So that's what we've been saying over and over again. I'll point out I can say that a little bit differently. That if I restrict myself to the alternative space, then having minimal type 2 error for a fixed type 1 error, so if I lock that in place from the beginning, minimizing the type 2 error in the alternative space is equivalent to saying we maximize the power. Okay, and if we do that across every test considerable, so if I can have more power, i.e. less type 2 error, for any theta I consider in the alternative space, I'll say that as being uniformly most powerful. So I have more power there. That's our terminology. And so oftentimes we write that down as UMP, and that's what that means. So UMP, we'll get around to it, write it all down specifically, but what we're really saying is that we're minimizing the type 2 error rate in the alternative space. So the alternative where the alternative is true, and so you don't want to make an error there. Okay, so this is the whole Stat 101 thing. Everybody's running around and turning the crank on thresholding p-values. And this is the mathematical justification for doing that. I want to say a lot about this, but there's a lot of technicality in this proof that we're going to have to go over. And I don't want you to get all caught up in all the technicalities when you're trying to assess, is this the right thing to do? So there's two different ways you can think about this lesson. Can you rederive it, regurgitate a proof, understanding why every line is correct in the proof? Or you can understand whether or not this is something that you want to be doing in the first place. There's two things to understand there. And so just because you understand every line of the proof doesn't mean that you understand when to apply this and when not to. You don't know which argument even necessarily to use as to why you would do this versus something else. And so two big things to consider. So if you've seen any of my midterm finals, QEs, a lot of times I'm trying to get around to both of those things. Do you understand what you're doing as a practitioner? And do you understand formally what you're doing from the mathematical side? So we need to understand both of those things. But let me just kind of walk through some notation. So in the book, they write down the sup over theta element of h naught, I'm just reading math, of the power function is equal to alpha. So let's just remember what these little creatures are. So this is the power function. What is the power function? It's the probability of being in the rejection region. So probability, x is an element of the rejection region. So just like in our test last time, we had x's that conform to rejects. In the binomial example, we had two different cases, and we could see how the power function was influenced by changing the decision from x equal to 5 or x equal to 3, 4, or 5. So that rule right here, we're going to have to get around to what that rule is, but Neyman and Pearson will describe it for us. They'll give us a specific rule. So this is the probability of x in the rejection region. Remember, x is governed by theta right here, and this is taking a supremum over theta element of the null. If you'd like to replace this with the maximum, go ahead. They're not the same. So one is a limiting version of the other one. So sometimes you might not be able to attain the point in the maximum, but you can limit into it. I don't really care if you understand that fully. It's a subtle point. But if you'd like to replace this with max, that's perfectly fine for me. So you can replace it here as well. Being able to deal with those technicalities is important if you're doing functional analysis. But I don't think it's important to understand this proof. Okay, so this supremum is akin to the maximum function that we've already been talking about. Apologies for them confusing you and jumping back and forth. Anywhere you see a maximum, I suppose you could replace it with a supremum in the book. Sometimes you would be talking about the maximum. The maximum is attainable. Sometimes that means max, and sometimes it means something else. So don't be blown away by it. So they have two different notions that they jump back and forth in their proof. I would say it's fine if you just stick with this right here. So the maximum of the power function, so the highest probability of rejecting happens somewhere in the null space. So previously, for our old example, we had some example like this where x came from this, and I wanted to test theta less than or equal to 1/2 versus theta greater than 1/2. So in the previous lecture, we did this, and I ended up saying x is equal to 5 to find the rejection region. So all stuff from our last lecture. So theta is a probability. It goes between 0 and 1. For this thing right here, I drew some curve that looked like this. Confused myself for a long time by drawing the wrong picture. This was rather flat right here. So this was theta to the 5, was this curve right here. This was 1/2. This is the null space in all of this. This is the power function. The maximum happens here. So this is tilting up in the null space. So that's this value. And I don't remember the exact value, but I remember it was about 0.3, somewhere around there, 3%. That's this thing, okay? Turns out in my picture, right here, these look about the same. So I could be talking about all of the other stuff less than some value. So if I fixated something, I maybe said 0.3 from beginning, might be talking about that point. But I could also be talking about these other values over here. Now, it really doesn't matter in one case which one you talk about. So I want to just go back and I want to reflect on the likelihood ratio. So this stuff is what governs the Neyman-Pearson lemma. And so what we've said is the maximum likelihood ratio test is this sort of test where I construct maximum of the likelihood restricted to the null region compared to the maximum of the likelihood with no restriction. Okay. This number, I call it lambda x. It's equivalent to lambda tx, where that's a sufficient statistic. We have a theorem, easy to prove, factorization theorem. This number is bounded by some number between 0 and 1. Okay, all very good. We've also convinced ourselves that this is equivalent, if you pick a fixed threshold right here, this is equivalent to fixing the type 1 error. It's the exact same. This defines some rule. X lives in some rejection region for this criterion to be true. The rejection region is defined to be the x's that satisfy this constraint. That's the rejection region right here. And there's some probability that those x's will be there. And so the maximum of that thing in the null region is called alpha, the size of the test. Oftentimes this number is picked to be 0.05. And that will relate to some threshold right here. Okay, so in terms of the normal example, a lot of times we end up looking at x bar minus the hypothesized value. or the limit of that hypothesized value. In the one-sided case, you'll always notice you plug in a number. That's what this limit is really about. It's looking at the most extreme value on there, the most informative one. Dividing by the standard error and seeing if that's above some critical threshold. So if you're doing the one-sided case, I believe Sierra told us that 1.645 was this number, and that would relate to a 5% error rate, type 1 error rate. So this ratio is Neyman-Pearson. It's really what's governing everything. I will want to say a couple other things. Let's just invoke some likelihood principle thinking. This is ratios of likelihoods, this criterion. And that's supposed to be good. I promise that as being a good thing, looking at ratios of likelihoods, that's very good. I like it. Bayesians kind of do something like it. They multiply by some penalty function. They'll have a prior in there. Hopefully it's not just any old prior. You have real reasons for picking it. Hopefully those have desirable properties, and all the calculations come in the form of ratios. So Bayesian posterior gets normalized by something in that likelihood function. You integrate over it along with the prior. But that comes in the form of ratios, and I've always maintained that's a good thing. So maybe that means that this is always a good thing. And so if you've been paying attention to some of my arguments for a while, a lot of times I don't love p-values. I've got problems with them. But I've advocated that likelihood ratios are good to look at. So aren't p-values just looking at likelihood ratios? And you might think of it that way. And I would say, yeah, you kind of are. So where's my big gripe? I'll say this. This is the big deal. So it's using this threshold right here. Notice that this is just one-sided. And so this is kind of assuming something about the functional form of this right here. And this would be a reasonable thing to threshold if this was monotonic, this function. So it's always trending in a certain way. It's either going up or it's going down. And so I can threshold because I know everything else is just more extreme. And that's a reasonable thing to do. I don't have any problem with that. I've also shown you an example where in the one-sided case for hypothesis testing, the non-Bayesian and the Bayesian agreed. In fact, the posterior probability on the null space that the Bayesian computed was equivalent to the p-value. And that agreement happens, or closely happens, when this function is monotonic. And you should recognize that maybe this is a reasonable criterion if it's monotonic. So you want to worry about the cases where this function is not monotonic. And that's where you hear all of the complaints. You don't see big gripes when this thing is monotonic. The Bayesian and the p-valuist, basically equivalent to this problem right here, are thresholding in similar ways. So I'll just make a statement that when this is not monotonic, just because you're using a likelihood ratio, that's probably not necessarily a good thing. So I want you to think about what you do when you compute p-values, that there's always this region of more extreme. So the more extreme region, more extremia. And so it's easy for us all to agree when our functions are more extreme, when we're dealing with a monotonic function and we're talking about more extremia. We're always talking about the same direction. But if you change the monotonic property of this, then we don't know what it means to be more extreme. And we get a little bit confused over that statement. So big controversies happen when this is not monotonic. Let me just make a note. When monotone, no big controversy. But when not monotonic, if you like this criterion, people like you and me won't agree. So I can just tell you. So just looking at one side of something when it's monotonic is not good enough. So when not monotone, there is controversy. So be careful. That's where it all creeps in. So that's the big deal. The way that the Neyman-Pearson lemma is set up and how they extend everything in the book might set you up to not think about this early on. But that's the big gripe in all of this. Okay, so those are just some precursors. So you can stick with this throughout everything, but if everything is monotonic, and in the case that they set up, this condition right here, looking at everything that's less than alpha in the type 1 error rate, won't hurt your power on the other side. So if I start looking at a test that has less than type 1 error rate alpha, that won't decrease my power. It won't increase my type 2 error rate on the other side. Think about that picture that I drew, where I have this power function. So if I ended up building in a rule that lessened my type 1 error rate, I would increase my power in the alternative space. I would decrease that error rate. That trade-off would work in my favor. And so in the simple versus simple case, I don't know if it's really worth distinguishing these two things, but I will point out that in our proof, the hypotheses that they're going to consider, they start here. This is called the simple versus simple thing. So this is just one data point, and this is one data point. That's the simple bit of it. So I'm not comparing intervals to each other, I'm just comparing two things. What they end up doing is they'll end up taking this pointwise evaluation and extending it over the number line maybe in one direction, and they'll take this point and extending it over the other direction. And they'll end up saying that basically all the theory that governs this pointwise evaluation, the simple versus simple, extends itself to the one-sided test. That's true. And you don't lose the monotonicity property and all the good things that happen in Neyman-Pearson. However, when you end up comparing the point against the rest of everything, so the interval against the point, the monotonicity property goes away. So it's in that sharp null test that we all complain about, argue about. The Bayesian has special treatment that provokes a lot of questions. I don't know if they're right, I don't know if it's a good thing to do, but at least the questions are there. All the questions that need asking require some form of an answer. If you don't have a good one, I don't like your test. This stuff I already don't like in the point null test, and it's simply because this is not monotonic. They'll try to disambiguate things, and they'll lead in with a property, unbiasedness of the test, and say if we put this condition down, then maybe we can recover something from all of this theory. I'll say I'm not so sure about that. So I'm a little skeptical. I haven't seen it work convincingly enough. I think there are applications maybe where it can work. But in general, that's not where I land on the debate. We'll talk more about that later. Okay, so terminology, I think it's fine to stick right here. We'll talk about this other thing that they invoke. Basically, when you're doing the point versus point thing, there's no problem with decreasing your type 1 error. Okay, we're back again. We had a technical glitch with our camera. I'm going to pick up on the lecture. I think that I was just ultimately saying something about the power functions that were right here. Hopefully I concluded in a reasonable way. What I do want to show you in the Neyman-Pearson lemma as we get going, so the Neyman-Pearson lemma, at least the proof in the book, is discussing the simple case. It's going to extend this case to the one-sided case. by extending the point comparisons to two different sets. They will eventually try to extend this to this two-sided case, but I'm not sure how far I got into my explanation of everything, but in the two-sided case, this function is not monotone, and that causes a lot of grief. So that's a big problem for us. And so they're going to have to build in an extra condition, and it kind of changes everything. Neyman-Pearson lemma says this. So at least in the simple versus simple form, these 2 points being compared to each other, X is in the rejection region, and they define what the rejection region is for you. It's right here. So if I'm given X, and I'm given theta naught and theta 1, I can compute whether or not this bound is true. And this bound is specific for some value of K, and that value of K is positive. And then I have the complement side of this. If you're bothered by this not having the equal sign, go ahead and drop it in, if you'd like. And if you'd like to pull off the equal sign right over here, that's fine as well. No big deal, one way or the other. X is assumed to be continuous in all of this, so the probability measure and the integrals over these functions never change if I just remove this one point. So this is the complement of that. So this is the rejection region complement. So either you're in it or you're not, and I have these two opposing conditions. One of these things is true. We've been saying over and over again that the max likelihood ratio test is the Neyman-Pearsonian thing. And we've just written down this condition right here. I want to point out that this right here is precisely this same thing in disguise. So they're written a little bit differently. And the threshold is expressed differently. I want to just point out that the difference in all of this is what I'm maximizing over. So in the max likelihood ratio, I'm maximizing over the null in the alternative space, the whole space in the denominator, and it's bounding this constant between 0 and, it's bounding this ratio between 0 and 1. This condition is very similar. There's a one-to-one mapping. That's what I mean when I say that they're the same. They're isomorphic to each other. So same sort of condition. For any value C over here, I can figure out what K is. And there's going to be a one-to-one relationship, whether or not this is true and this is true. So this is always going to be true when this thing is going to be, I guess in this case, well, this is the rejection right here. So this is true when this is less than C. There's some value of K that I can get and some value of C that I can compute so that these are true. This is true when that is true. Okay, let me just say that real quickly. Notice that the maximums in all of this is completely superfluous because in this simple versus simple test, we're just calculating over one data point. And so that's the easiest maximization you can ever do. There's only one choice. So I'll just write out that max, my likelihood function, over H naught, so theta's in H naught. Remember what H naught is, it's just that one point right here. And instead of maximizing over the alternative, I'm going to change this a little bit. And I'm going to maximize this only over the alternative space. And I'm going to put the 1 right here just to be consistent with this notation. So really what the book has done is they've changed all your notation on you. But this thing right here is just a maximum over that one point. So this criterion is a little bit different from this one because of how I'm normalizing it. You'll notice that this number right here can be anything between 0 and infinity. I'll point out, how do I compute my likelihood function? That's just f theta given x. That is that functional form. And this is just f theta. I can't help myself. X given theta. X given theta. So how did I compute the likelihood? I wrote down the the sampling distribution's density right here. I'm thinking about just one data point in all of this. Or I'm thinking about this thing as being a sufficient statistic that I'm plugging in and I've computed from all of the data. And this is the distribution of that sufficient statistic, whatever x is. And so these are proportional to each other and they're coming in as a ratio. And so whatever that constant is that I feel like arbitrarily multiplying by, I would do the same thing in both the numerator and the denominator and they cancel. So when I maximize over these one data point, it's just this, fx given theta naught over fx given theta 1. Right here. In this number lives between 0 and infinity. So I've just kind of changed the way I'm normalizing this and what the meaning of this number is. Personally, I like playing around with these sort of things because I can usually tell somebody what big means, can tell them what the biggest number is. So this might be a little bit more human friendly, but this contains exactly the same information. And so that's what k is right here. So k is an element of that. And you can convince yourself now that there's a relationship between c and k. Nobody will ever ask you to compute it, what it is, but you can conceptualize that it's there. So this condition right here is the maximum likelihood ratio test stat in disguise. And that's what this says, just with all the notation being different. The second part in all of this is just stipulating something that's constant throughout the whole proof. That the maximum power, I should just say this part, or I should say that the probability of x being in the rejection region is computed to be alpha. And this is going to be fixed. Whatever f is, whatever all of these hypotheses are, I can pick k such that that's true. So I pick k such that that's true. So if you're wondering what changes up here, that's an actual value of k. I can't tell you what it is until you tell me what these distributions are, but I could, at least in theory, compute it for you. And so Neyman-Pearson is saying, if you got these two things true, two statements that we're going to make. So a test satisfying both of these two things is uniformly most powerful. Let me write that down. That's supposed to be a big deal. I said this at the beginning of the lecture, that what I mean when I say that is that it has the least amount of least type 2 error rate. So look at what we've got. Fixed type 1 error rate, likelihood ratio. The implication is that in the alternative space, your power function is higher, i.e. your error rate in the alternative space is lower. That's what this says. So, and it always keeps appending this. Everything's size alpha, all the way through. So, because it's fixed through k. Okay. If there exists a test, this is the if and only if part. So it's saying that tests satisfying this are uniformly most powerful, i.e. for a fixed type 1 error rate, the type 2 error rate is minimized, and it doesn't matter how you pick these. That's the U part, the uniformly across the space. So if there is a test satisfying this, i.e. it's uniformly most powerful, it's this one. That's what it says. So this is really just an if and only if statement right here. So if a test satisfies this, we're always going to carry 2 with us. It's size alpha. We're talking about size alpha tests. So if out of that class of size alpha tests, this is true, uniformly most powerful. If there is a uniformly most powerful test out there, it's equivalent to this one. Okay, so that's an if and only if thing. I've kind of stipulated, I think this is all very good. I like likelihood ratios if they're monotone. And so in this case right here, everything is monotone. So everything works out great. No big gripe over here. We're going to prove this. And I'm going to show you at least the master equation that you need to understand to be able to prove this. So here's just a little bit of notation that we're going to conclude with. And once you understand this inequality, the proof is seamless. So let me just give you some notation. I'm going to say, I'm going to have a test, delta x. Okay, so I take my data point x and I plug it into this thing. And I'm going to tell you what this test is. This test is going to return either accept or reject for us. So it's going to tell me whether or not I want to accept or reject this thing. And it's going to do it by using an indicator function. So this test is going to be a 1 if this condition is true. Is greater than k fx given theta naught. So that's a reject. And this will be the other side of it. Fx given theta 1 less than k fx given theta naught. This condition. Okay, so really I've just encoded everything this says with a 1 or a 0. Give me all those numbers and you've calibrated k such that this is true, I can plug everything in and get back a 1 or a 0. So this is the Neyman-Pearson test. As a reminder, that's the likelihood ratio test stacked in disguise. Okay, here's another test. And if you've played around with math, this looks like a very typical proof technique. So, some other test. I don't care what test this is. This is also going to take on values, 1 or a 0. But I'm not going to tell you what the criterion is right here. I'm going to say that it's a coherent test, that these two things don't overlap each other. So it's only going to tell you a 1 or a 0. That's all I'm going to tell you about this. So we're going to at least be coherent and consistent in our thinking. But this test right here is some other test from that. Okay. Later on, we're going to assume that this test is uniformly most powerful. We're going to prove that it's that test. It's got to be this one. That's this other part of the proof. And we'll show very early in the proof that this test right here is also uniformly most powerful. So we're going to do two different things, two different directions in this proof. Show that this is a UMP test right here because it satisfies the likelihood ratio test statistic criterion. And we're going to end up showing that if any other test also has the same good properties, it's uniformly most powerful, also size alpha, that this test is that one. It has to be. How we're going to prove that is just going to require this equation. So this is the big breakthrough equation. Try to convince yourself this is always true. They just state this in the book. So the book states this. And if you miss why this is true, nothing else will make sense to you. Because this inequality gets regurgitated about 17 times. Okay, it says this. Make sure I got my directions right. So this is the big master equation in all of this. This thing right here looks like a bunch of terms that appears here. So everything is being pulled over just one side. It's this side, subtract that side. These are my two tests, okay? I don't know much about this test right here. I haven't told you anything about it. I do know about this test, however. And so to verify this equation, just makes you re-examine these inequalities. That's where the inequality comes from, and the conditions here. So we can get this, and from what we conjectured in the first place. All you have to do to convince yourself of this is to go through it for every possible case. This is what I do when I see these things. If I can enumerate it, I do it. So let's take a 1 right here. So if this thing is a 1, then I know this is true. So I know this thing is bigger than that. This thing is positive right here. I don't know much about that. If this was a 1, this is 0. That's equal to 0, so check mark. 0 times something positive is positive. If this were a 0, I have 1 minus 0, which is 1. This thing is positive, that's positive. Check mark. This is what the book thinks is too obvious to explain in a sentence, and it really is. So, but this is everything that's going on. Okay, if this was true, this thing was a 0. If that were a 0, right here, then this is a 0, check mark. If this were a 1, it's two different cases right here. This is negative. That's true. This is negative. Negative times a negative is positive, check mark. In all cases, that's true. So that's always true. That's the fundamental equation. Let me show you one last bit that they do with this thing. And from this, you could probably convince yourself that these two things are true. This is all we use. So what we're going to do is we're going to integrate over this equation. So we're going to integrate over this. Integrating over x. These things are fixed for us. So we know something. This is greater or equal to 0. So this thing's always positive, so on average, it's positive. Gotta be. This reduces into 4 terms. So this has 4 terms once you expand it. They all look like this. Each one of the terms looks like an indicator function multiplied by one of these. So all of the 4 terms involve one of these tests. I'll just write down J right here if you'd like. It's one of those 2 things. Times fx given theta, and it's going to have one of these 2 points in here. So I'll denote that right here. Dx. Now I want you to think about what that is. So this is just an indicator. Those are our 2 tests. It's one of those 2 things. And this is our density. And we understand this is the probability of delta x given theta I. So this is the expected value, if you will. I'll type down my superscript right here. So this is the expected value of an indicator function. Expected values of indicator functions are probabilities of those indicators. If that seems confusing, go back to what a Bernoulli is. That's exactly what it is. So the expected value of a Bernoulli is the probability of that indicator. That's the same thing going on right here. What is this thing right here? This is just x being in some sort of rejection region, right? That's what that test is indicating. So this thing right here is the power function for whatever that theta is. That's what that is. So what we're going to do is we're going to examine this integral. We're going to break this into 4 different power functions. And we're going to use what we know about the inequalities, this stuff right here, to ascertain that the power function for this test is bigger than that one. That's what we're going to prove. So if this test came from this stuff, the power function here will be bigger than the power function for that. If this is the second part of this, if the power function is uniformly most powerful already, what we're going to figure out is that this thing right here has to always be a 0. That's in the second direction. So I'll come back, I'll walk through those technicalities, but understand this and understand how this breaks into the 4 terms. Probably write them all down. And then everything gets concluded. So more next time. Tomorrow I'll have that lecture out for you. I want to also cast a reminder that on Friday I'll come in and I'll just kind of reserve the time to answer some questions. I think we can start up at 3:30. Maybe we can start early. Maybe come in at 3 and just do some Q&A for a while. So if you have midterm questions about all this stuff, how does it relate to Bayesian testing, whatnot, then would be a good time. So until tomorrow, thanks a lot, kids.